Hello everyone, my name is Kyeongha Kwon. I'm an assistant professor in the School of Electrical Engineering at KAIST. I'm excited to have the opportunity to present the findings of our recent research on flexible electronic systems in healthcare. My background. I did my bachelor's, master's, and doctoral degrees at KAIST and spent 3 years as a postdoc associate at the Center for Biointegrated Electronics at Northwestern University. Then last December, I joined the Circuit Division in the School of Electrical Engineering at KAIST as an assistant professor. So my area is broadly circuits and systems design. Within that, I work on the development of flexible electronics in healthcare. COVID-19 highlights the growing role of new medical technology, especially in the field of non-contact remote patient monitoring via users' wireless medical devices. Remote patient monitoring solutions collect medical health data and vitals such as blood pressure, heartbeat, and sweat variables as biomarkers of different diseases from the user's wearable devices. Often in the form of medical wearables and apps, users transform their smartphone into a mobile lab for real-time diagnostics and disease surveillance. The low-cost, user-friendly platform enables mobile testing at the point of need for healthcare, such as in mobile clinics for disease tracking or home use. Data is then uploaded to cloud. Then physicians and hospitals can remotely monitor these patients and take action if required with AI-powered health and wellness monitoring. This medical ecosystem can play in fighting the spread of infectious disease, and our main interest area is the development of novel biointegrated medical devices, thereby remotely delivering digitalized medicine and healthcare. In fact, there's a variety of wearable devices commercially available in market today, but most of the devices involve primitive level of biointegration, usually in the form of a rigid block of electronics, loosely strapped to the wrist. However, in order to digitize human signals accurately and continuously, we need to reformulate the electronics into biocompatible forms so that we can overcome mechanical mismatch between soft human body and rigid electronics. Therefore, our research centers on the development and verification of the flexible medical devices that simply adhere to the human body. The following slide will introduce an example of flexible electronics developed to analyze sweat as a source of biomarkers. Sweat is a non-invasively collectible biofluid that hosts a broad range of biomarkers, which provide a clear advantage over invasive blood sampling. Recently, various sweat patches have been proposed to provide sweat collection and colorimetric analysis of different biomarkers in sweat. However, in interpreting sweat chemistry from the color development, sweat rate and loss are critically important, as sweat chemistry is known to depend on the flow rate and total loss of sweat. Thus, to monitor the sweat flow rate in real time, we designed a microfluidic channel to allow the collected sweat to flow through a narrow passage and then we create a thermal flow sensor that incorporates a thermal actuator and two thermistors, one for measuring the temperature upstream and the other for downstream, relative to the flow direction. These components laminate on top of a thin silicon structure that interfaces with a short, straight sweat channel. The flowing sweat below transports the heat from the actuator directionally downstream, thereby creating the temperature difference between up and downstream, and hence establishing a simple linear relationship between the temperature difference and the flow rate of sweat. As a result, we could develop a wireless electronic patch that can measure the temperature difference in upstream and downstream with an electronic circuit, convert it into a digital signal, and then wirelessly transmit the data to user interfaces so that user can check the data in real time using a smartphone app. The patch can be easily attached to the skin with flexible circuit board and soft silicone encapsulation layers. On body testing, the patch accurately measured the sweat rate in the range of 0 to 5 microliter per minute, which is considered physiologically significant. The sensor can directly measure the flow of sweat and then use the information it collected to quantify the total sweat loss. Moreover, the device, combined with advanced microfluidic architectures and colorimetric chemical reagent, provided pH measurement and determined the concentration of chloride, creatine, and glucose in a user's sweat. These indicators could be used to diagnose various diseases, such as diabetes, kidney dysfunction, and metabolic alkalosis. This work has been published in Nature Electronics, so you may refer the paper for more details. As another application, we applied the platform to monitor the flow through a shunt. A shunt is a tube inserted surgically that prevents brain damage by draining excessive fluid into the abdomen. Unfortunately, shunts have extremely high failure rate, but there is no convenient mean to diagnose shunt malfunction, except our platform. To demonstrate our platform, clinical study involved placement of the device at a distal location along the shunt above the clavicle, and also at an off-shunt location as a comparison in 7 patients who implanted the shunt above the clavicle. In the absence of flow or at an off-shunt location, the temperature difference between upstream and downstream is around 0. However, at on-shunt measurement site, data shows difference between downstream and upstream temperature around 0.2 Celsius degree. So that we say that our platform can detect and alarm the shunt malfunction. This work has been published in Nature Partner Journal, Digital Medicine. So you can refer the paper if you're interested. Future plan is to combine our platform with a drug delivery patch, embedding microfluidic architectures with microneedles enables new degrees of freedom for transdermal drug delivery. As a specific example, by applying thermal actuation to a micro-sized drug chamber, the resulting thermal expansion enables drug injection via microneedles into the skin. However, this system cannot control or calculate the exact dosage, as well as the drug release rate. So we envision to combine our flow sensing platform with skin interfaced drug delivery patch to achieve controlled drug delivery. This system can measure real-time release rate and calculate the exact dosage, thereby delivering the correct medication at the correct time. Such a technology can organize dosage of medication by day or time, especially for patients with dementia or Alzheimer's disease. It can help caregivers and family members keep track of patients' medication schedule. Let me conclude my presentation. Our research team aims to transform emerging technologies, including advances in areas such as sensor network, mobile communication, bioengineering, and artificial intelligence, to provide digitalized healthcare. Our flexible wireless electronics and cost-effective user interfaces digitize human signals continuously and accurately, thereby bridging temporal and spatial gaps in healthcare system between rich and poor countries. In the future, medicine and healthcare will be digitized. Nearly invisible, continuous, and wireless medical devices will be a big part of this revolution. Thank you.